Hello, my name is Micaela Cadena, and in this video I present the Poincaré-Bendixson Theorem and its proof. Here, I present the structure of our video. We will first set conditions and preliminaries to announce the theorem. We will also go through some additional results which will come in handy for the proof of the theorem. Afterwards, we will make a couple remarks about the theorem and present an example. Let f be a function in Rn to be continuous and locally Lipschitz. Then equation 1 has a unique solution. We denote by phi t of x0 the solution of equation 1 with initial condition x0, which would be the solution evaluated at time or parameter t equals 0. And t belongs to I of x0, where I of x0 is the maximal interval of the solution of 1. Then the flow map would be defined by writing phi t of x0 equal to x of t. Our first definition is the definition of orbit. Given a point in Rn, which would be a solution, the full orbit through x would be defined by the set of solutions such that t belongs to the maximal interval. We also define forward and backward half orbits. The forward half orbit is given by this set, which would be the set of solutions for which t belongs to the maximal interval, but also t is bigger or equal than 0, while the backward half orbit would be the set of solutions such that t belongs to the maximal interval, but we'd have t to be less or equal than 0. We also define what an omega limit set is. We say that a point seed is an omega point of the forward half orbit if there exists some t sub n that tends to positive infinity, if we have that x evaluated at this t sub n goes to z. The omega limit set then is symbolically characterized in this way. But thanks to characterization of closed sets by sequences, by convergence of sequences, it follows that the omega limit set is a closed set. And we can also define this set in terms of orbits. It would be the intersection of the closures of the forward half orbits evaluated at y, where y belongs to the full orbit of x. We also define that a set of Rn is said to be invariant with respect to equation 1 if phi t of x belongs to A for every x in A and every t in the maximal interval of x. So now we're ready to announce our theorem. Let's consider the autonomous dynamical system such that x of t belongs to omega, which is a subset of R2. And we define a function that goes from omega to R2 to be locally Lipschitz on an open set omega. That is, our system goes from R2 to R2. Then, for a solution x of the system, we will consider the forward half orbit a subset of a compact set, which is a subset of omega. Thanks to the characterizations of the omega limit set in terms of the forward half orbit, we would also have that the omega limit set is a subset of K. Therefore, we would have that the omega limit set is compact, and by the continuous dependence on initial data theorem, we would also get that the omega limit set is an invariant set. Under the above assumptions, if the omega limit set contains no equilibria, then the omega limit set is a single periodic orbit, which we would call a cycle. Moreover, if X transverses itself the omega limit set, we say that this solution is periodic, or the distance between the solution and the omega limit set will tend to zero as t goes to infinity. So what are we saying with this theorem? In basic terms, or simpler terms, we might say that if we have a region which is bounded and compact, and we have a solution for this dynamical system, we will have either that this solution is periodic or it will converge to a periodic solution. So this theorem is not about doing calculations, but rather is about the behavior of the solutions of the dynamical system. So now we will introduce two results that would be necessary for the proof of the theorem. So that's why we'll first cover the definition of transverse line segments. We have that L is a transverse line segment if is a closed line segment contained in omega such that F is nowhere parallel to L on the segment. In fact, we might say that every non-equilibrium point of omega lies in the interior of some transverse segment. Now we can introduce the crossing order lemma, which states that if an orbit crosses a transverse segment L at least twice, then E orbit is not closed. Moreover, if it crosses L several times, we will have that the crossing points are ordered along L in the same order as along the orbit. The proof of this lemma is easily followed by looking at this image. Here, we will consider this trajectory to be the orbit, and we will consider this segment to be our transverse segment, which is called L. So now the orbit will cross the segment through the point A, and it will do it a second time through the point B. Now, one alternative would be that B is equal to A, but in that case, the orbit would be already closed. So, if the orbit would cross the segment again through a third point, which we will call C, and if we wanted C to be in the near of A, that is, to be between A and B, as in the order ACB, what will happen is that this part of the orbit would intersect this segment of orbit that goes through point B, and that can't be possible because of uniqueness. So the only way for it to go through this segment again is if it's in the near of B, as in the order ABC. Therefore, the lemma is true. And that's what I tried to write here in this sketch. We have that between two successive crossings A and B of L, the arc of the orbit from A to B, together with a subsegment of L, bound to a region that the flow can only enter. That means that after A and B, when I say that it can only enter, is that it will follow the same directions, like the same sense. In this case, in the case of the image, is a clock sense. It will continue with that sense. Okay? It can only enter. The orbit cannot re-enter a neighborhood of A without crossing the arc, which is impossible by uniqueness. That's what I said previously. Hence, no return to A and the stated ordering in the lemma. The second result that we will present is a corollary. A point A on an orbit is a omega limit set point of its own orbit if and only if the orbit is closed, that is, if it's periodic. For the proof, the if part is immediate because if the orbit is closed, we would have that any point A on an orbit would be an omega limit set point of its own orbit by the definition of omega limit set. For the only if part, we're gonna suppose that a point A lies on an orbit and is also an omega limit set point of that same orbit. Then, if A is an equilibrium, then the orbit would be the constant one, hence it would be closed because a set with a point is a closed set, and we are done. Otherwise, we're gonna choose a transverse segment L that goes through the point A. And because A is a omega limit set point, the trajectory returns arbitrarily close to A. Therefore, at some future time, it must cross L at a point B near A. And if the orbit is not closed by the lemma, by the previous lemma, we will have that A is different than B. By the crossing order lemma, after crossing L at B, the trajectory cannot subsequently enter any neighborhood of A. Thus, A cannot be an omega limit set point, which would be a contradiction. Therefore, we must have that the orbit is closed. And in this graph, we can also try to explain the proof of this corollary better. We have, maybe it's not the best graph, but I tried to make an orbit. Here, the line would be the orbit that goes through the point A, that crosses the segment L, and it crosses it again through B. If it were to cross it again at a point C, in order for it to be near A, would be to go back through this path between A and B, here through this curve, which is not possible thanks to uniqueness. And another way would be to go through this subsegment of L, AB. But then the trajectory would be closed, the orbit would be closed. So with this image, I try to say that there's no way to return near A after crossing this point B, because then the orbit would be closed. And this is the idea that we use to build the contradiction in the previous proof. With both results, we can already prove our main theorem. Here I have rewritten the Poincaré-Bendixson theorem in a more concise way. And for the proof, we will consider two scenarios. We will consider X star, a point in the omega limit set, and we will choose a transverse segment L through X star. We will also consider the complete orbit through X star. And the first case we're gonna work with is X star belongs to the forward half orbit of X. If that were true, then we would have that X star is an omega limit set point of its own orbit. And by the previous corollary, that would mean that the orbit through X star is closed. So we would call this periodic orbit gamma. but by the invariance of the omega limit set, it implies that gamma must be a subset of the omega limit set. But also, we have a hypothesis in our theorem, and that is that the omega limit set has no equilibrium point. And we can say that the omega limit set is the set of all points that belong to the forward half orbit. This condition forces that the omega limit set must be none other than gamma. For the second case, we will consider that X star it's not in the forward half orbit of X. So even though that might be true, then we are going to consider the full orbit through X star, and we will prove that this full orbit must be closed. So let C sub 0 be a omega limit set point of the full orbit through X star, and we're gonna let L prime be a transverse segment through Z0. Let's clarify that this is a misuse of notation. I should have used maybe Z star, but with Z0, I don't mean to say that this is an initial condition. It's just a point in the omega limit set. So we will suppose for contradiction that the full orbit through X star is not closed. Then by the lemma we saw, that implies that the full orbit through X star crosses L prime infinitely many times, approaching Z0 from one side. So now we will pick two successive crossings, A and then B, along L prime. Now, because the omega limit set is invariant and it equals to the set of omega limit set points of the forward half orbit. Now, because the omega limit set is invariant and it equals to the set of omega limit set points of the forward half orbit, and because both points that belong to this orbit, and this orbit is a subset of the omega limit set, we would get that both A and B are omega limit set points of the forward half orbit of solutions X. Hence, we will get that the forward half orbit crosses L prime arbitrarily close to B, entering the shaded region bounded by the piece of orbit between A and B and the segment of L prime here. It would be around here. This region. And by the ordering lemma, once the flow enters that region, it can't return to the neighborhood of A, but that contradicts that A is an omega limit set point of the forward half orbit. Therefore, we must have that the full orbit of X through X star is closed. And we're gonna denote this periodic orbit by gamma. And as in the first case, we also use the fact that the omega limit set is invariant, and so is gamma. So now gamma is a closed invariant orbit containing X star that's also in the omega limit set. And there are no equilibria in the omega limit set, so we must have that both sets are equal. So what's left to prove is that if the solution is not periodic, that is, if if we can conclude that gamma is equal to the omega limit set, then we're going to say that the distance between omega and the solution will tend to 0. So now, because x star belongs to the omega limit set, by its definition, there exists some Tn that goes to infinity with x of Tn that goes to x star. And for large n, each x of Tn lies on the interior of the fixed transverse segment L through x star. So we have the forward half orbit crosses L in a sequence of points converging to x star. By the continuous dependence on initial data, this behavior forces that the forward orbit to accumulate and hence to approach the invariant set omega. Thus, we get our desired result, which was that either the solution x is periodic or that its distance to the omega limit set tends to 0 as t tends to infinity. This concludes the proof. Now, what happens if the omega limit set contains equilibria? Well, since an important hypothesis of the Poincaré-Bendixson theorem is that it doesn't contain any equilibria, well, we have the possibility that the omega limit set is just a set containing a single equilibrium point. And in that case, by the definition of omega limit set, we would get that x of t tends to x star. But more generally, the omega limit set could have one or more equilibria which are connected by paths, which are solution orbits, and we call these cases heteroclinic or homoclinic connections. And here I have an example where I show what would be a homoclinic path, which has a infinity shape, and here our equilibrium point would be right at the center at 0. Finally, here we present a brief example of the application of the theorem. So we're going to consider the system of differential equations here. And in this image, we have depicted a vector field along with solutions for the system for these three initial conditions. And one can intuitively, well, not so intuitively, but we can say that sine of t and cosine of t are solutions to the system. And we can check that for points inside the circle, inside the unit circle, we will get that the solution will spiral off into that region. I mean, the solution will start spinning around that. No, the solution will orbit around that unit circle. But for points outside the unit circle, the solution will spiral off to infinity, which is this segment, this red segment that we see right here. And so what we're seeing is a spiral that, so we're seeing is a solution that spirals off. So we're seeing that for certain initial conditions, the trajectory is barreling outwards, but into the unit circle, while for others is spiraling outwards to infinity. And here's what we call an unstable limit cycle, which is what we try writing here. Here we have stated that x is equal to sine of t, while y is equal to cosine of t, and we consider points outside and inside of the unit circle and see the behavior. And finally, here I have put my references for creating the materials, the images, and also the way I stated the results. So thanks a lot for watching.